This is the Spatial Media Expert Series presented by Skyrim.ai. In this episode, we demystify spatial media formats from point clouds to neural radiance fields and what is next.
Welcome to the Deep Dive. Today, we're plunging into a world, well, where you don't just watch a moment, you step inside it.
Yeah, exactly. Imagine, flying around that game-winning shot, pausing time.
Seeing it from the player's perspective, or maybe even from right above the hoop.
Right. Traditional 2D video, as amazing as it is, it's always been like looking through this fixed window, hasn't it?
Totally. But what if that window could just disappear, letting you explore the scene like you were actually there?
Yeah, that's precisely the challenge and the incredible opportunity we're really digging into today.
Okay.
We're tracing the evolution, the whole journey of capturing 3D movement over time, starting from, cumbersome volumetric video.
Right, that early stuff.
All the way to the revolutionary concept of spatial media, which is heavily driven by AI now.
So our mission today is really to unpack the key breakthroughs, right? Figure out how we got here and look at how companies like Skyrim.ai, for instance, are just fundamentally changing the game for how we experience real-world events in 3D.
Exactly. And you, listening, you'll learn not just about the tech itself, the nuts and bolts, but why this shift actually matters, why it's important for everything from watching sports, like you mentioned, to all sorts of professional applications.
Okay, so we're charting the path from those early, maybe clunky 3D capture methods.
Right, the ones with explicit geometry.
Through to how neural networks and AI have really, truly transformed what's even possible.
And culminating in these innovative approaches that are, setting the stage for the future of immersive content. It's quite a journey.
It really sounds like it. And like any good journey, we kind of need to know where we started. So where did we begin? What was that first attempt to step beyond fixed window into what we initially called volumetric video?
Okay, so volumetric video at its absolute core is the art of capturing 3D movement over time.
Right.
Think of it like this. Traditional video gives you, maybe, a shadow on a wall. It's flat.
Yeah, just 2D.
Volumetric video aims to capture the entire sculpture in motion, with its full depth, its volume.
Oh.
So you can actually walk around it later, virtually.
Yeah.
It's about seeing the whole picture in 3 dimensions as it changes.
The whole sculpture. That's a really powerful way to think about it. A huge shift in perspective. But how do you actually capture a moving sculpture? My first thought is just like an army of cameras.
You're absolutely spot on. That's traditionally how it worked. In practice, it typically involved using many, many cameras.
Right.
Recording a subject, or maybe a whole scene, from basically all angles simultaneously.
Okay.
And then all that footage, all those different views, have to be painstakingly reconstructed. Algorithms crunch the data to build a full 3D video.
And the dream, then, is video you can experience from literally any viewpoint.
Exactly. As if you're physically present in the scene, moving around, not just stuck looking through one fixed camera lens.
So it's capturing a dynamic 3D model, frame by frame almost, not just a static object. I can only imagine the sheer amount of data involved in that.
Yeah.
And just how do you even store it? That must be a massive part of the puzzle. What were the practical challenges there?
Oh, absolutely. You've hit on the fundamental challenge right away. The way this 3D data is represented, how it's stored and structured.
Ooh.
Oh, it affects everything.
Like what specifically?
We're talking the raw file size, obviously, but also the visual quality you can achieve, how easily you can edit it later or stream it over a network.
Yeah, streaming must be a nightmare.
And critically, the latency. The speed of playback. Can you see it live or near live? Or is there a long processing delay? Early approaches, while they were groundbreaking for their time, they often produced these absolutely huge files, incredibly hard to manage.
Even though they captured a lot of detail, I assume?
Oh, yeah. The detail could be fantastic, but the practicality, that was the issue. Newer approaches have constantly been aiming to shrink that data down, speed up the rendering.
Right.
Sometimes, though not always, that meant maybe sacrificing certain fine details to gain efficiency.
So there's always this kind of dance, isn't there? A trade-off between getting that incredible fidelity, that perfect sculpture, and making it practical enough to actually use, to stream, to interact with.
Exactly right. It's fidelity versus practicality. A format that stores every tiny detail might look absolutely stunning, photorealistic even.
Yeah.
But it can be so heavy, so data intensive that you just can't use it in a live, interactive setting. It's just too much to handle in real time.
Okay.
Conversely, you might have a more efficient format that streams beautifully maybe even in real time.
Right.
But perhaps there's some loss of texture detail, or the resolution isn't quite as crisp.
I see.
So understanding this whole evolution, this journey from the early days of things like point clouds and meshes,
Which we'll get into.
all the way to more recent innovations like Gaussian splatting and, crucially, neural fields, that's essential to really grasp how we've arrived at today's solutions.
Right.
And why this new generation of tech, what some are calling spatial media, is finally starting to unlock truly scalable, high-quality 3D video.
Okay, that sets the stage perfectly. Let's dive into that first phase then, what we're calling the legacy era, the time of points, polygons, voxels, literally trying to build reality brick by digital brick. What was the core challenge with these explicit geometry approaches?
The main challenge, the fundamental issue, was that these legacy formats tried to explicitly capture the precise shape, the exact geometry of everything in the scene.
Everything, like every little detail.
Pretty much, yeah. The goal was an exact digital replica. And while this approach could guarantee a really high degree of realism, you were essentially getting a faithful 3D model.
Yeah.
It also resulted in absolutely enormous data sizes. One of our sources used a great analogy. It was like hauling around raw marble sculptures.
I like that.
They're rich in detail, no doubt, but just incredibly cumbersome to move, to store, to process.
So trying to digitally recreate, say, a player making a shot with every fold in their jersey, every muscle movement.
Exactly. Or a bustling city street where every leaf, every pebble, every stitch of clothing on every person is explicitly defined by points or polygons. The data just explodes. It quickly becomes unmanageable, especially for complex or dynamic scenes.
Hauling around raw marble sculptures, that image really sticks. Okay, so let's break down these early foundational formats. First up, point clouds. What exactly are we talking about there?
Right, point clouds. They are essentially just thousands or often millions of colorful dots scattered in 3D space.
Just dots.
Yep. Each individual dot has an X, Y, and Z position, defining its location in 3 dimensions. And typically it also includes color information RGB values.
Okay.
Imagine throwing a handful of multicolored confetti up in the air and freezing it. That 3D scatter of confetti where each piece has a specific color and position. That's a pretty good way to visualize a point cloud.
Interesting analogy.
They're often the raw output you get directly from 3D scanners or these multi-camera rigs we talked about. Just a dense collection of points that sample the surface of people or objects in the scene. It's like this constellation of individual data points that, when you look at them all together, start to form a recognizable shape.
So like 3D confetti, what were the upsides and downsides of capturing reality this way?
Well, on the plus side, point clouds can capture incredibly fine details. Because you're just recording individual points, you can get a very precise representation of a surface, right down to, tiny imperfections or textures.
Okay, high fidelity.
But the major downside is that they are inherently unstructured. They're just these discrete points floating in space with no built-in connections between them.
Right, just dots.
Which means, firstly, they require huge storage space, especially if you want high resolution.
Yeah.
You're literally storing the coordinates and color for every single one of those millions of points.
Wow.
And even for empty space sometimes, if you're trying to capture a whole volume rather than just surfaces. Plus, that unstructured nature makes them kind of difficult to edit or manipulate directly. How do you, say, smooth out a surface that's just made of disconnected points?
Right, I can see that. Okay, so if point clouds are just the dots, unstructured and massive,
Right.
how did we start to make sense of them? Turn them into something more, usable? I'm guessing that's where meshes or polygons came into the picture?
Precisely, yeah. A mesh is essentially what you get when you start connecting those dots.
Okay.
Take that raw point cloud data, and then algorithms try to figure out which points should be connected to form a surface. Usually they draw triangles or sometimes other polygons like quads between adjacent points.
So like stretching a skin over the points?
Exactly. Think of it like stretching a net or a piece of digital fabric over that scattered confetti. These connections, these triangles, form the mesh. And this mesh transforms those discrete points into continuous surfaces. This makes the data generally more compact than the raw point cloud. And crucially, it makes it ready for rendering in standard graphics pipelines. You can apply textures, image maps onto those surfaces.
I see.
It's basically the connect the dots version of reality. The goal is to define the outer shell, the surface geometry, of an object or person. Most 3D models you see in games or animation are built from meshes.
So it's definitely more efficient for rendering, makes sense. But what's the trade-off there? Are we losing something when we connect the dots like that?
There are trade-offs, yeah. While meshes are certainly more compact and much better suited for rendering with textures, generating them from those raw point clouds actually takes a significant amount of computational power. That process of figuring out the connections and creating the surface, it involves complex algorithms like surface reconstruction.
Right, it's not trivial.
And in that process, that simplification from points to surfaces, some of the very fine, nuanced detail that was captured in the raw point cloud can potentially be lost or smoothed over.
Oh, okay.
You're effectively simplifying the geometry to make it more manageable for graphics cards to draw. Plus, even once you have a mesh, editing it or deforming it, especially for dynamic movement like a person running, can still be quite complex if you want to maintain photorealism.
Gotcha. Okay, so we have points, the meshes connecting them. What about the third one you mentioned, voxels? We know about pixels in 2D, but what are 3D pixels?
Voxels are exactly that, volumetric pixels or 3D pixels. They're essentially little cubes arranged on a regular grid in 3D space.
Cubes.
Yeah, tiny cubes.
Yeah.
And each cube, each voxel, can have a property assigned to it, like a color, or perhaps a density value, indicating if it's filled or empty.
Oh, okay.
So point clouds are like stars in space, and meshes are like a skin draped over those stars.
Yeah.
Voxels are more like a 3D grid of tiny building blocks.
Yeah.
You divide the entire volume of space you care about into this fixed uniform grid, say a 256 by 256 grid of cubes, and then you specify the properties of each tiny cube within that grid.
So kind of like building something out of digital Legos, but with super, super tiny, maybe invisible Legos making up the whole scene.
Exactly. That's a great analogy. Tiny Legos filling up space.
Wow.
The advantage of voxels is that because the space is uniformly divided into this grid, it makes certain operations really easy. Things like physics simulations or collision detection become simpler.
Ah, I can see that.
You know, objects occupy specific cubes, and it's clear where one object ends and another begins based on which cubes are filled.
But there's always a but.
But they suffer from a massive, massive problem. They tend to explode in memory size if you want high detail.
Explode.
Yeah, think about it. Imagine needing a tiny cube for every wrinkle on a face, or every individual strand of hair on someone's head, or every blade of grass on a field. The number of cubes required becomes astronomically large very quickly.
Right, because you're filling the whole volume, not just the surface.
Exactly. You need cubes even for the empty space inside an object, potentially. So for volumetric video specifically, pure voxel representations were generally less common than point clouds or meshes, simply because the data sizes were often prohibitive for capturing dynamic, detailed scenes. Though some systems use them, especially in fields like medical imaging, like CT scans, or for very dense reconstructions where that volumetric information was key, they are truly the volumetric pixels, but their appetite for storage was often just too much.
Okay, so these legacy formats, points, meshes, voxels, they were foundational, but clearly came with some pretty significant challenges, especially around data size and processing. But despite that, there were still some impressive real-world examples, weren't there? Can you give us a sense of how these systems were actually used despite those limitations?
Oh, absolutely. Even with the challenges, the potential was so tantalizing that people built some really impressive systems. Two prominent examples definitely come to mind. First, you had Microsoft's mixed reality capture studios. These are pretty serious setups. They use something like 106 cameras mounted all around a dedicated stage to record a performance.
106 cameras. Wow.
Yeah, it's a lot. And from all that multi-camera data, their software computes a detailed 3D point cloud, and then usually a mesh of the person for each frame of the video.
And the result?
The result is a highly detailed hologram, a 3D video of, say, an actor, a musician, an athlete, whatever was recorded on the stage. You can then view this hologram in 360 degrees using VR or AR headsets.
And the quality was good?
The fidelity is genuinely fantastic. You can see incredibly fine details like every fold in their clothing, sometimes even individual strands of hair. It looks really solid. But as you can probably guess,
incredibly data heavy.
Extremely data heavy. And the whole process requires these specialized, expensive studio facilities. It's not something you can just set up anywhere easily.
Right. Yeah, 106 cameras. That sounds less like a setup and more like a whole permanent installation. What were the real world headaches beyond just the data size of trying to deploy something that massive?
Oh, the logistical headaches were immense. I mean, just think about the calibration. Getting 106 cameras perfectly synchronized, knowing their exact position and orientation down to the millimeter.
Right.
That's a huge task.
Right.
Then there's the lighting. You need perfectly even, consistent illumination across the entire stage from all angles so the colors and textures match up when you reconstruct.
Yeah, shadows would mess things up.
Exactly. And then just the sheer volume of cabling, the power requirements, the controlled environment you need. It really limited where and how these systems could be used, mostly just in these dedicated controlled studio environments.
Okay, so Microsoft was one big example. Who else was pushing this?
Another major player, especially in sports, was Intel with their TrueView system.
Yes, I remember hearing about that. The NFL replays.
That's the one. It became famous for its be the player 360-degree replays, particularly in the NFL, but also other sports. They used a similar approach. Dozens of high-resolution, like 5K, cameras positioned strategically all around a stadium.
Capturing the whole field.
Capturing the key action areas, yeah. And they used this data to produce volumetric replays, often based on point clouds.
And the data scale there, still huge.
Absolutely staggering. Get this. According to reports, each 30-second clip captured by Intel TrueView could require up to 1 terabyte of raw data just to process.
1 terabyte for 30 seconds. That's insane.
It is. And it wasn't instant either. They needed dedicated servers, often installed right there on site at the stadium, just to crunch all that data and spit out a cohesive 3D video replay that could then be used in the broadcast or apps.
Wow. So these systems like Microsoft Studios and Intel TrueView, they definitely demonstrated the incredible potential, didn't they? Like letting fans replay a goal from any angle they choose on a mobile app. That's cool.
And very cool. A glimpse of the future.
But they clearly ran headfirst into some serious limitations. What were the biggest hurdles that really prevented this kind of volumetric video from becoming mainstream back then?
Well, the first, and probably the most obvious one, was just the sheer scale of the files and the bandwidth needed to move them around.
Right, that terabyte for 30 seconds.
Exactly. When you're capturing potentially millions of points or polygons per frame, and you have 30 or 60 frames per second, the raw files are just enormous.
Yeah.
Studios that produced this content, places like Metastage in LA or Dimension in London, they had to develop specialized codecs and compression tools just to make the files manageable enough to be streamed at all.
And even then, it was probably a challenge for a regular internet connection.
Absolutely. Imagine trying to stream even a heavily compressed version of that terabyte clip to millions of fans simultaneously during a live game. The infrastructure just wasn't ready for that kind of load on a mass scale.
Yeah, that makes sense. And I can only imagine the processing power needed on the back end before you even get to streaming.
That's the second major limitation. The complex, compute-heavy processing pipelines involved.
Okay.
Turning all that raw footage from dozens or over 100 cameras into usable point clouds and meshes. It's incredibly computationally intensive.
What's involved?
It's usually a multi-stage process. You have complex algorithms like multi-view stereo trying to figure out the depths from all the different camera views. Then you get careful alignment of all those camera feeds. Then surface reconstruction algorithms try to build the 3D shapes. And then you often need texture mapping to apply the visual details, the colors and textures onto those shapes.
Wow, that sounds like a lot of steps.
It is. And critically, this was not a real-time process back then. Not even close, usually.
How long did it take?
It could easily take hours, or sometimes even days, to process just a few minutes of high-quality volumetric footage. Remember, Intel TrueView needed those dedicated on-site servers crunching away for each clip. Microsoft systems similarly required substantial processing time to produce a finished hologram.
So you couldn't get instant replays in 3D?
No, not truly instant. You were always looking at delayed post-process content, maybe minutes or longer after the action happened.
So essentially, you couldn't really use it live in any meaningful way during a broadcast, which I guess leads to the third major limited interactivity for live use.
That's exactly right. Because the files were so massive and the processing took so long, these legacy formats were mostly useful for pre-recorded content or maybe slightly delayed playback.
Right.
You could capture a volumetric highlight, process it offline, and then let people play it back from any angle later. But doing that fully live with, say, sub-second latency like you need for a truly live broadcast feel, that was basically out of reach.
Why? What were the bottlenecks for live?
Well, the data was just too heavy to stream live without extreme compression. And compressing that kind of complex 3D data effectively in real time was incredibly difficult with the technology back then. Plus, the capture setups themselves needing tens or hundreds of cameras, often in very controlled studio environments, made it really hard to scale the technology to every stadium or every event, or to move beyond a fixed stage area.
Yeah.
It remained a very specialized tool. Impressive, but not something broadly deployable or ready for mass adoption in live scenarios.
So these incredible but incredibly cumbersome marble sculptures from the legacy era, the potential was crystal clear, but the practicality was, frankly, a bit of a nightmare.
That sums it up pretty well.
So what came next? How did the field try to move forward from this? How did we even begin to, lighten that load without completely sacrificing the magic of 3D?
Okay, so that brings us to the next really fascinating development on this path, a technique called Gaussian splatting.
Gaussian splatting. Okay, what's that?
This emerged more recently as a really intriguing innovation, specifically aimed at creating high-quality 3D representations that could be rendered much, much faster than previous methods.
Faster rendering. Okay, how does it work? Is it still points or meshes?
It's different. If you think of point clouds as these crisp individual points,
Yeah.
then you can think of Gaussian splats as more like fuzzy balls or maybe ellipses of color and transparency that when you have millions of them, they sort of blur together to form surfaces.
Fuzzy balls. Like 3D paintballs.
Kind of, yeah. Maybe think of it like an impressionist painting. Up close, you might just see individual dabs or blobs of paint.
Right.
But when you step back, they all blend together smoothly to form a cohesive, recognizable image. Gaussian splatting works a bit like that, but in 3D.
Okay, that's a great visual. So instead of precise points or sharp triangles, we're talking about these fuzzy blobs. How does this actually work technically to create a 3D scene?
So each sample in a Gaussian splatting scene isn't just a point location. It's actually a tiny 3D Gaussian function. Think of it as a little 3D blob of color that has a defined softness or spread, a fall-off.
Okay, a blob with properties.
Exactly. When you project millions of these fuzzy blobs into a 2D image plane, like onto your screen, they blend together based on their properties, shape, color, transparency, to form what looks like a smooth, solid surface.
And what are these properties?
Each Gaussian splat typically has a position in 3D space, a shape, often represented as an ellipse that can be stretched or squished, a specific color, and a level of transparency or opacity.
Right.
And the rendering process basically involves splatting these millions of 3D blobs onto the 2D screen very efficiently. The key advantage here is that this splatting process, this rendering, can be extremely fast.
Why is it so fast?
Because it leverages mathematical operations that are very, very friendly to modern graphics processing unit GPUs. It's essentially like painting these blobs onto the screen super rapidly, avoiding some of the more complex step-by-step ray marching calculations that other methods, like early neural radiance fields, needed.
Okay, so GPU-friendly fuzzy blobs.
Yeah.
Did someone manage to really prove this concept out? Was there a big moment that put Gaussian splatting on the map for real-time rendering?
Absolutely. There was a huge breakthrough moment in 2023. A research paper from a team led by George Stratakis at INRIA, a French research institute, demonstrated this incredibly well.
What did they show?
They showed that by representing scenes using these 3D Gaussians, they could achieve real-time 3D view synthesis, meaning rendering new views of the scene at high resolutions like 1080p and at frame rates well over 100 frames per second.
Over 100 VPs at 1080p, that's truly real time.
Oh yeah. Their method, which became known simply as 3D Gaussian splatting, was a sensation. It actually won the Best Paper Award at SIGGRAPH 2023, which is the top computer graphics conference.
Wow. Why was it such a big deal?
Because it was arguably the first time that someone had combined state-of-the-art visual quality, really photorealistic results, with true real-time rendering speeds for generating these novel views of a 3D scene.
Okay.
It kind of shattered the long-held assumption in some circles that you absolutely needed explicit geometric models like meshes to get high-quality 3D rendering. Gaussian splatting proved you could achieve stunning photorealism much, much faster by just cleverly blending these fuzzy blobs.
That's a massive acceleration, especially that real-time aspect at high quality.
Yeah.
What kind of imagery can this produce? And, what were the immediate limitations or caveats of this new approach?
The imagery you can get from Gaussian splats is genuinely impressive. You can capture a scene, say, take a bunch of photos of a building or a room or an object from different angles.
Right, using just regular photos.
Yeah, often just ordinary photos. Then the algorithm optimizes a set of potentially millions of these colorful, fuzzy ellipsoids to represent that scene. When these optimized ellipsoids are splatted onto the screen from a new viewpoint, they look remarkably photorealistic. It's essentially a different, often more efficient way to store the 3D information. Not as triangles or dense voxels, but as these adaptive blobs that can cover space quite effectively.
Adaptive blobs, I like that.
Yeah, they kind of automatically adjust their shape and size to represent surfaces efficiently.
Yeah.
It preserves some of the advantages of continuous volumetric data because each splat has that smooth fall-off.
Right.
But it avoids wasting processing effort on large chunks of empty space. Unlike maybe a dense voxel grid. It's like painting an object with spray paint. Instead of placing individual bricks, you cover the surfaces efficiently with just enough spray to give the illusion of solidity.
Okay, so it sounds like a really clever compromise, balancing quality and speed. But
Yeah.
you mentioned caveats. What were the downsides? Where did it still fall short, especially for those truly dynamic applications like live sports?
Right. The primary caveat, especially with the initial groundbreaking methods, was that Gaussian splatting was designed primarily for static scenes.
Ah, okay. So things that don't move.
Exactly. Capturing an environment, like a room or a street or an object that isn't changing over time, that's where it excelled. If anything in the scene moves significantly, people walking around, trees blowing wildly in the wind, the basic approach tends to struggle.
Why does movement break it?
Because the optimization process assumes the scene is fixed. When things move, the positions and properties of the optimized Gaussians become incorrect for later frames, leading to blurring or ghosting artifacts.
Okay.
Now, researchers are very actively working on dynamic extensions. There are already papers out on dynamic Gaussian splatting trying to handle moving subjects.
Right.
But the core strength demonstrated initially, and where it really shone, was in the super-fast rendering of a fixed scene.
So maybe great for capturing environments, but not yet the solution for, say, a fast-moving athlete.
Not inherently, no.
Yeah.
Not without those more complex extensions. And even with the capture side, while companies like Niantic, the Pokemon Go creators, have touted that maybe anyone with a decent smartphone could scan an environment and produce a splatted 3D scene.
Yeah.
Which is fantastic for democratizing 3D capture. It's still typically a process that's done offline. You capture the data, then process it, usually in the cloud or on a powerful machine, to optimize the Gaussians. It's not really designed for generating these representations on the fly for live events, at least not yet.
And the training time, is that instant?
No. While the rendering is super fast, the initial training or optimization step, taking the input images and figuring out the millions of Gaussian parameters, that can still take some time, maybe minutes or longer, depending on the scene, complexity, and the hardware.
Okay. So Gaussian splatting sounds like this really intriguing middle ground. It kind of ditched the need for explicit geometry like meshes, which was a big step.
Right.
But it still kept an explicit representation of the scene, just with these clever blobs instead of points or triangles.
That's a good summary, yeah. An explicit representation, but a novel one optimized for rendering speed.
And it certainly proved that real-time rendering of high-quality scenes was possible, shattering some previous assumptions. That's huge.
Yeah. Absolutely. It raised the bar for rendering performance.
But it wasn't quite the full solution for truly dynamic, real-time, volumetric video, was it? Especially if the core method struggled with movement and still required an offline optimization step.
Correct. While it was a major advance in rendering static scenes, and the compression techniques for potentially dynamic splats are still being developed, it wasn't the fundamental shift needed for fully scalable, live, dynamic volumetric content.
So for that, we needed something even more revolutionary, something that maybe didn't rely on any explicit representation.
You're absolutely right. We needed something else entirely. And that brings us to a truly revolutionary technology that arguably flipped the script on 3D representation when it burst onto the scene around 2020. Neural radiance fields.
Neural radiance fields. Okay, I've definitely heard this term buzzing around, flip the script. That sounds like a really seismic shift. How exactly do neural radiance fields differ from everything we've discussed so far? It seems like we're moving beyond even the fuzzy blobs now.
It's a completely different paradigm. Utterly different, unlike all the prior methods we've talked about.
Yeah.
Points, polygons, voxels, even those Gaussian splats. Neural radiance fields store absolutely nothing explicitly about the scene's geometry or appearance.
Nothing explicit. So what do they store?
It's an implicit representation. The scene is stored implicitly within the weights of a trained neural network.
Wow. Okay, unpack that. A neural network holds the scene.
Yeah. The core metaphor that's often used is this. Instead of storing every single brick and stone of a castle model,
Right.
we train a small brain, a neural network, that can perfectly imagine what the castle looks like from any possible viewpoint, any window you choose to look through.
Okay. That's a fascinating idea. How does it work in practice?
In practical terms, a neural radiance field is a neural network, typically a fairly simple one called a multi-layer perceptron, or MLP. You feed this network two pieces of information as input: a 3D coordinate, an XYZ point in space, and a 2D viewing direction, where you're looking from.
Okay, position and direction.
And the network then outputs two things for that specific point in space, viewed from that direction: the color, RGB value,
Yeah.
and the density. Like, how opaque is that point in space?
Color and density for any point I query.
For any 3D point you ask it about, yeah. The network learns this function that maps any 3D location and viewing direction to a color and density based on the input images it was trained on.
So it's essentially learning the entire light field of the scene rather than building the scene itself brick by brick or even blob by blob. That's truly mind-bending.
Precisely. It's learning a continuous function representing the scene's radiance and geometry to actually render an image from a specific camera viewpoint.
How do you get a picture out of it?
You simulate rays traveling from the virtual camera out into the scene.
Oh.
For many points along each ray, you query the neural network to get the color and density at those points.
Okay.
Then, using techniques from classical volume rendering, basically summing up the color contributions along each ray, weighted by the density, you can calculate the final color for each pixel in your image.
Wow. So simply put, a neural radiance field learns to paint a 3D scene.
That's a good way to think about it. You feed it a collection of 2D photos of a real scene taken from different viewpoints.
Right.
And the network trains itself to understand the 3D structure and appearance so well that it can then generate or paint a new, previously unseen photo of that same scene from basically any new angle you ask for.
And it does this without ever explicitly creating a mesh or a point cloud or voxels.
Correct. It doesn't build an intermediate geometric representation. Instead, it acts like this kind of black box. You ask it, if a camera were positioned here, looking this way, what color should this pixel be? And the network figures it out based on its learned understanding of how light travels through that 3D scene. That's why it's called a neural radiance field. It's modeling the radiance, the light, throughout the volume.
That is truly a fundamental shift in thinking about 3D representation. Okay, so when this first came out in 2020, what was the initial impact? And what were the immediate limitations? Because I'm guessing that kind of magic usually comes with a catch, especially early on.
Oh, there was definitely a catch. But first, the impact. It was profound. The quality of the novel views that the original neural radiance fields paper produced was just stunningly realistic, photorealistic.
Better than previous methods.
Often, yes.
Yeah.
Especially for scenes that were traditionally very difficult for multi-view stereo methods. The algorithms used to build meshes from photos. Things like objects with very fine geometric details or surfaces that were transparent or highly reflective.
Ah, okay.
Neural radiance fields could often learn to represent these complex appearances much more accurately than methods relying on explicit geometry reconstruction. It was a real wow moment for anyone working in computer graphics and computer vision.
Okay, so amazing quality. What was the catch? Speed?
Speed was the massive catch. The original neural radiance field models, while producing beautiful results, were excruciatingly slow.
How slow are we talking?
Training a single neural radiance fields network on a single scene could take hours, or sometimes even days,
Yeah.
even running on a powerful GPU.
Always. For one scene.
Yeah. And then rendering just a single image from that trained network could take several seconds,
Yeah.
or sometimes even minutes, depending on the resolution and the complexity.
Okay, so definitely not real time.
Not even close. So it was this incredible proof of concept. It showed what was possible if you threw enough computation at the problem, often outperforming prior methods in terms of pure visual quality. But it absolutely wasn't practical for any kind of interactive use case back then. You couldn't possibly use an early neural radiance fields for, say, a live sports replay if you had to wait minutes just to render one frame from a new angle.
Right. Stunning results locked behind a wall of computation time. But this is where that astonishing progress in speed you mentioned earlier comes in, right? Because I know this technology hasn't stood still. It seems like it's come a long way very, very quickly.
It has been truly astonishing. The pace of progress in just the last couple of years has been incredible, specifically focused on making neural radiance fields faster.
Like what?
Well, a major breakthrough came in 2022 from researchers at NVIDIA. They introduced a technique called instant neural radiance fields, often abbreviated as instant NGP.
Instant neural radiance fields, what did that do?
It used a really clever trick involving a specialized data structure, a multi-resolution hash grid encoding, to represent the scene much more efficiently. This innovation allowed them to train a high-quality neural radiance fields network in a matter of seconds or maybe minutes instead of hours or days.
Seconds or minutes, down from days.
Exactly. It was a monumental speed-up. The impact was so significant that Time magazine actually named NVIDIA's instant neural radiance fields one of the best inventions of 2022.
Wow. From a slow lab curiosity to a bust invention in such a short time frame that really speaks to the potential people saw in it. What did that breakthrough mean for actually using neural radiance fields?
It was transformative. It fundamentally shifted neural radiance fields from being this fascinating but mostly academic lab curiosity into something that you could actually start thinking about using in real production pipelines.
Right.
Suddenly, the idea of taking a bunch of photos or even a short video clip and getting a navigable 3D model out in just seconds or minutes instead of waiting days, that became feasible. It opened up the possibility for all sorts of applications beyond just pure research.
And was it just NVIDIA making progress?
Oh no, not at all. It sparked a huge wave of research across the field. Companies like Google and Meta, Facebook have also been heavily involved, publishing their own increasingly faster and better neural radiance fields variants. The whole academic community jumped on it.
So lots of different approaches now.
Yeah, you see papers focusing on even higher quality, enabling things like incredibly detailed 3D human portraits, or even capturing entire city blocks with neural radiance fields. Others are prioritizing raw speed even further, or adding special features like the ability to edit the scene after it's been trained or handle dynamic elements better.
And I believe there's a whole ecosystem of tools that have topped up around this now, making it more accessible for people who aren't necessarily deep researchers.
Absolutely. That's been another key factor in its rapid adoption. A whole ecosystem of software tools has emerged. A prominent example is Nerf Studio, which is an open-source framework developed initially by researchers at UC Berkeley.
What does Nerf Studio do?
It provides a unified platform that makes it much easier for users, even non-experts, to train various different types of neural radiance fields models, visualize the results in real time through a web viewer, and experiment with the technology.
So it lowers the barrier to entry.
Massively. These tools hide a lot of the underlying complexity. They allow users to just plug in their own images or video footage, choose a model, click train, and get a 3D scene out that they can explore.
Right.
As a result, neural radiance fields has gone from this niche academic idea in 2020 to something that hobbyists, artists, and developers are actively experimenting with today, just a few years later.
Yeah.
This incredible progress in speed and accessibility has really brought the magic of neural radiance fields much closer to everyday practical application.
Okay, that's fantastic progress.
Good.
But despite all these incredible speed-ups and new tools, what are some of the persistent challenges that even these classic fast neural radiance fields still face? Especially when you think about something as demanding, dynamic, and fast-paced as, say, live sports broadcasting.
That's a great question. Because even with all the speed improvements, the classic neural radiance fields approach, even the fast ones, still have a few significant hurdles, particularly for that kind of application. First, they traditionally still require quite a lot of input images, captured from many different angles all around the subject or scene, in order to train a high-quality model.
So you still need that dense camera setup, similar to the old legacy methods. You can't just use like one or two cameras.
Generally, no. You still need fairly dense coverage to get good results, especially for complex scenes. So the capture hardware requirements can still be significant.
Okay, still data hungry on the input side.
What else? Second, and this is a really big one for dynamic content like sports, each new scene or each significant change in the scene typically requires training a brand new neural network.
Yeah.
It's not like you train one universal sports understanding model that can then instantly generate neural radiance field for any new play or any new game environment. You essentially have to retrain the network, or at least fine-tune it significantly, for each new piece of action you want to represent.
So if you have a football game with, say, hundreds of individual plays, does that mean potentially hundreds of new networks to train? That sounds like it could still add up to a lot of computation, even if each one trains faster now.
It definitely could, yeah. That per scene optimization cost is still a factor, especially if you need results extremely quickly.
Okay. Any other limitations?
Well, there's rendering latency. While it's much, much faster than before, rendering a single frame from even a highly optimized neural radiance fields might still take on the order of, say, tens of milliseconds on a good GPU.
Tens of milliseconds? That sounds pretty fast.
It is. It's generally okay for maybe a single viewer interacting with it. But if you imagine needing to render unique views for potentially thousands or millions of interactive viewers simultaneously, those milliseconds per user can quickly add up and potentially affect the overall latency and scalability of the system.
Right. Scaling it to a mass audience interactively is still a challenge.
It can be. And finally, perhaps the biggest challenge for classic neural radiance fields: dynamic content. Things like athletes running, jumping, colliding. This kind of complex motion traditionally breaks the core assumption of the original neural radiance fields formulation, which was really built for static scenes.
Because the network assumes the world isn't changing.
Exactly. The network learns a single static representation. When things move, that representation becomes invalid. Now, there's a ton of active research going into dynamic neural radiance fields trying to model how scenes change over time.
Okay.
But it's still a very active, challenging area of development. Getting real-time, high-fidelity capture and rendering of complex, fast-moving scenes using purely classic neural radiance fields approaches remains a significant hurdle.
Okay. So the original promise was incredible quality. The speed has improved dramatically, which is amazing. But these specific challenges remain, particularly for highly dynamic, real-time scenarios like sports needing lots of input data, per scene training, potential rendering latency at scale, and the inherent difficulty with fast motion for the classic approach.
That's a fair summary of the state of play for classic neural radiance fields, yeah.
But this, it seems, leads us to a bigger conceptual shift. You mentioned this idea of implicit neural representation and the dawn of this neural fields era. It sounds like we're moving beyond just making neural radiance fields faster into a completely new way of thinking about the problem.
Yes, exactly. This is the truly fundamental shift that neural radiance fields kicked off, and it's really groundbreaking. The core idea is you don't explicitly capture the shape or appearance of an object. Instead, you capture its essence, its volumetric appearance, and maybe even its behavior, implicitly within the weights and structure of a neural network.
Right. The network is the representation.
Precisely. And this concept, this move towards implicit neural representations, was the crucial stepping stone to what people are now calling the neural fields era of 3D content.
Okay.
The new goal for next-generation volumetric video systems became, what if we could design a system that outputs not explicit geometry, like points or meshes, but rather a highly efficient, optimized neural field representation directly, one that's specifically designed to be efficiently streamed and rendered in real time.
So not just using neural nets to process data into all formats, but making the neural net itself the final product, the thing you stream.
Exactly. This is where the next generation truly takes flight. It's moving from just reconstruction of old formats towards intelligent inference of new neural native formats.
And this brings us right to the cutting edge, to what you're calling Generation 3, and specifically to examples like Skyrim.ai's ecosystem. How is Echo fundamentally different from everything we've discussed so far? Is it just a faster, better neural radiance fields, or is it something else entirely?
Skyrim. AI's Echo is positioned as a prime example of this new third generation. And based on descriptions, it represents a profound departure from prior approaches. It's not just an incremental improvement.
How so? What's the core difference?
The absolute core difference is this. Unlike legacy systems that output point clouds, meshes, or voxel grids, and unlike even classic neural radiance fields methods that might internally use a neural net but are still often evaluated by how well they reconstruct traditional views, Echo, as described, doesn't produce a human-readable 3D model in the traditional sense at all.
No mesh, no point cloud.
Apparently not as its primary output. Instead, it generates a highly efficient neural representation directly, a representation that's optimized specifically for real-time streaming and rendering. In fact, Skyrim.ai specifically uses the term spatial media to describe this new class of content, precisely to distinguish it from the older forms of volumetric video that relied on explicit geometry.
Spatial media. Okay, so it's not just a faster way to make volumetric video, it's a fundamentally different kind of output, a whole new format.
That seems to be the key claim. It's not just a new way to process the data, but a whole new language for representing dynamic 3D reality. That's a powerful idea.
It really is a new language for 3D video.
And the key innovation, based on their materials, is that Echo's output is natively neural. It's designed from the ground up to be a neural representation. It apparently doesn't need to be converted from an intermediate point cloud or mesh or anything like that.
Ah, okay. So it skips that intermediate step.
It seems so. It's as if the system speaks this new, compact neural language for 3D video directly, rather than relying on the old building blocks of voxels or the connect the dots of meshes or even the fuzzy blobs of Gaussian splats that we had before. This natively neural output is designed to be inherently more compact, more efficient, and more flexible for modern applications.
This sounds incredibly advanced. Can you give us some more concrete details about Echo's approach and what it can actually achieve in practice? What makes it work?
Well, while the specific proprietary details of Echo's internal format and algorithms aren't fully public, we can piece together some key aspects from their descriptions and announcements.
Okay.
Firstly, it's described as an AI-driven 3D reconstruction model. Crucially, this model has reportedly been trained on a massive data set of sports footage. They mentioned tens of thousands of captures.
Tens of thousands. That's a lot of training data.
It's a huge amount.
Yeah.
And this extensive training allows the AI model to develop a deep learned understanding of how sports actions typically look and unfold in 3D space, the physics, the common movements, the appearance of players, and environments.
And how does that training help?
It allows the system to infer a full, high-quality 3D scene from potentially much less input data than previous methods required. It can leverage that deep learned understanding to intelligently fill in the gaps, handle occlusions, and produce a complete 3D reconstruction, even if the camera coverage isn't perfect.
Okay, so less input data. Does that mean fewer cameras needed? Because that would be a huge deal for practical deployment in stadiums.
Exactly. That seems to be one of the major benefits they highlight. Skyrim.ai has reported that Echo can potentially reduce the required camera count by up to 2/3 for high-quality volumetric capture compared to traditional methods.
2/3 fewer cameras. Wow.
Yeah. So to put that into perspective, imagine a stadium setup that might have previously needed, say, 30 specialized cameras carefully placed around the field to get decent volumetric coverage.
Right.
Might now only need perhaps 10 cameras feeding into the Echo AI system to achieve the same or maybe even better volumetric output quality.
That is an absolute game changer for cost and logistics.
It really is. Fewer cameras means significantly easier and cheaper deployment in sports venues. It lowers the barrier to entry dramatically, making high-quality volumetric capture potentially feasible for many more leagues, teams, and venues than ever before. That's critical for widespread adoption.
Definitely. And I understand it also demonstrates real-time capability. That was the other big hurdle.
Crucially, yes. Reports indicate that Echo demonstrates real-time, or at least near real-time, reconstruction performance.
Okay.
This puts Skyrim.ai, and potentially others working on similar neural native approaches, firmly on a path toward enabling true live volumetric broadcasts. Imagine seeing a slam dunk in basketball or a crucial goal in soccer reconstructed and streamed immersively in 3D almost instantly after it happens.
That's the dream, isn't it?
It is. And Denny Breitenfeld, the CEO of Skyrim.ai, has described this coming shift in really dramatic terms. He's quoted as saying that with technology like Echo, we'll soon look back and realize we've been watching sports as if it were in black and white.
Wow, black and white. That's a bold claim. What's the analogy there?
The analogy suggests that once you experience sports volumetrically, being able to choose your own angle, pause and explore a play in 3D, experiencing it as if you're actually on the field or court traditional. Flat 2D replays and broadcasts will start to feel fundamentally limited, maybe even antiquated, like the difference between black and white TV and full-color HD.
Yeah. I can see that, a completely different level of immersion and understanding. It's a powerful metaphor. So going back to that idea of a new language, you mentioned this natively neural format. How does Echo's approach compare metaphorically to the older systems? Is it still just assembling pixels and points, or is it doing something more intelligent, more generative?
It definitely seems to lean more towards intelligent generation or inference. If you think about the older volumetric systems, metaphorically, they were like building a digital twin of the action, brick by brick, like voxels, or point by point, like point clouds, or maybe stretching a skin over points like meshes.
Right, very explicit construction.
Echo, on the other hand, based on the descriptions, sounds more akin to the AI dreaming the digital twin into existence. It takes a potentially sparse input signal, the footage from fewer cameras, and uses its extensive prior training, its learned knowledge, to intelligently reconstruct the full detailed 3D scene.
Dreaming the digital twin. Guided by data?
Exactly. That's the new kind of language it seems to speak. It's not just assembling the replay from the raw pixels available alone. It appears to be intelligently imagining or inferring the parts it can't directly see based on its understanding of physics and sports visuals, but always guided by and consistent with the actual footage that is available.
Okay, so it's crucial that it's not just hallucinating or making things up, right? It has to be grounded in reality.
Precisely. That's a really important distinction. It's not inventing new events or creating a different play than what actually happened on the field.
Yeah.
Instead, the idea is that it can intelligently infer things like depth or reconstruct parts of the action that were temporarily occluded, hidden from all camera views, by leveraging its vast learned knowledge of how bodies move, how balls fly, how players interact in these specific sports contexts.
Okay.
This learned inference is what seems to make it so powerful and efficient, allowing it to produce a robust, complete 3D representation from potentially much less input data than was previously thought possible.
The implications of this kind of neural native format, like Echo's spatial media, sound really profound. How does it specifically break those scaling limitations that have plagued volumetric video for so long and kept it mostly a niche technology?
It seems to attack those limitations on multiple fronts.
Okay.
Think about the scaling issue for capture first.
Right, the hundreds of cameras problem.
Exactly. If you wanted to cover, say, an entire league's worth of games volumetrically using legacy systems, you'd potentially need to outfit every single stadium with dozens, maybe hundreds of specialized cameras, plus install massive on-site processing servers, hire specialized crews.
Yeah.
The cost would be astronomical.
Completely impractical for most leagues.
Right. But with an AI-driven approach like Echo, if you truly only need a handful of cameras per venue, maybe just augmenting the existing broadcast setup. And if the heavy lifting of reconstruction is done by an efficient AI model, potentially running in the cloud, suddenly covering an entire league or even multiple sports becomes economically and logistically feasible. It dramatically lowers the barrier to entry for widespread deployment. It moves volumetric capture from specialized, expensive studios, potentially, into every major sports venue.
That's huge for capture. What about the other big bottleneck? Streaming this rich 3D content to potentially millions of users simultaneously. That's always been the ultimate challenge for truly immersive experiences at scale.
That seems to be another key advantage of a natively neural format. Because the neural scene representation output by a system like Echo is designed to be inherently lightweight and efficient. It's not a massive mesh file or a dense point cloud, but rather a compact neural encoding.
Right.
You can potentially multicast that compact data stream much more efficiently to millions of users over existing networks.
And then what happens on the user's end?
Then each user's device, whether it's a smartphone, a tablet, maybe VR or AR glasses, can take that compact neural stream and handle the rendering locally, generating the specific view the user wants in real time.
So the rendering load is distributed.
Exactly. This is far more scalable and efficient than trying to either pre-render every conceivable angle for every single user on the server side, which is computationally impossible at scale, or attempting to stream huge raw 3D geometry data like meshes or point clouds down to each user, which is often too cumbersome for current network infrastructures and consumer devices to handle smoothly.
Okay.
This approach, streaming a compact neural representation and rendering on the client device, potentially paves the way for truly interactive, high-fidelity live broadcasts at massive scale. It completely changes the economics and feasibility of delivering immersive 3D content to a wide audience.
So this fundamental shift towards AI-driven neural native spatial media means that those previously almost unimaginable possibilities for sports viewing live, interactive, immersive experiences for everyone are now actually starting to become reality.
It really seems that way.
It's clearly not just a tech novelty anymore. It sounds like the key that finally unlocks these immersive sports experiences that were just impractical before. So, zooming in a bit, what does this new era of spatial media mean concretely for the broadcast and production teams on the ground? How does it change their day-to-day?
The implications are potentially massive across the board for how sports are captured, how they're produced, and ultimately how they're consumed by fans.
Okay, let's break that down. First, you mentioned replays. How does this change replays?
Okay, first let's talk about real-time immersive replays. With efficient neural formats like Echo's spatial media, a highlight play, a goal, a touchdown, a home run could potentially be captured, reconstructed in 3D, and made available for interactive streaming just seconds after it happens live. Or maybe even completely live with minimal delay.
Seconds.
Yeah. Imagine you, the viewer, being able to instantly pause a pivotal play and then freely fly your virtual camera around it. See it from the goalie's perspective, from above the stadium, from the sideline, all in high-fidelity 3D, right there on your device, almost immediately after it occurred.
That's basically the ultimate instant replay, isn't it?
It really is. It's the fulfillment of what systems like Intel's TrueView started to promise with their 360-degree replays, but potentially taken to a whole new level of speed, quality, and accessibility.
And because the capture and processing are potentially cheaper and more efficient.
Exactly. This capability might not just be reserved for the one or two biggest highlights of the game anymore. It could potentially be available for every significant play because the cost and complexity of generating each volumetric replay could be dramatically lower.
That would completely transform how we analyze and relive key moments in a game. Okay, so instant ubiquitous 3D replays. What about giving the viewer more control over the live broadcast itself? Is it truly a choose-your-own-adventure kind of viewing experience?
That's definitely one of the most exciting possibilities.
Yeah.
The idea of choose-your-angle broadcasts.
Tell me more.
Instead of the traditional broadcast where a director in a truck is choosing the single camera cut that everyone sees at any given moment,
Right.
imagine a future where the primary broadcast feed is actually this live volumetric stream, this spatial media feed.
Okay.
Then, each individual viewer, through their app or device, could effectively become their own director. During a live basketball game, maybe you want to watch from a consistent sideline view for a while. Then maybe switch to a bird's eye view to see the court spacing, or maybe even get a virtual player's perspective during a fast break.
So I control my own virtual camera within the live 3D scene.
Precisely. Your viewing app would let you pan, zoom, and orbit your virtual camera anywhere within that live reconstructed 3D space. Legacy volumetric video hinted at this kind of freedom, for example. Some teams had apps allowing fans to control highlights.
Yeah.
But neural spatial video, with its efficiency and potential for live streaming, has the potential to make this kind of personalized, interactive viewing truly mainstream. It promises the ultimate personalized viewing experience, putting the power of the broadcast director right into the fans' hands.
That would be absolutely incredible for fans who really want to dive deep into the strategy or just see the action from their preferred angle. Okay, beyond the main screen, what about interacting with the game in other ways? Could we literally bring the game into our living rooms?
Yes. This opens up huge possibilities for interactive second screen experiences and especially augmented reality, AR.
How so?
Well, sports fans already love multi-screen experiences, right? Watching the game on the big TV, checking stats or social media on their phone or tablet.
Guilty as charged.
Right. So, with volumetric video becoming more accessible, imagine a second screen app or perhaps AR glasses that could literally let fans pull a live 3D representation of the game right into their own room.
Like on my coffee table.
Exactly. Picture viewing a miniature tabletop AR model of the soccer pitch or the basketball court, with little live 3D players running around, reconstructed in real time via this neural spatial media feed. You could physically walk around your coffee table and see plays develop from any vantage point.
That would be amazing.
And because these neural representations are potentially so efficient to stream and render, even a standard iPad or the next generation of AR glasses could potentially handle rendering a live volumetric feed like that.
Wow.
And think about the impact on analysts, too. In the studio, instead of drawing X's and O's on a flat telestrator screen, sports analysts could be using holographic replays that they can actually walk around inside. They could pause the action, point out player positioning in true 3D, and discuss strategy in a completely immersive, intuitive way. It could revolutionize sports analysis.
So it's not just enhancing the fan experience, it's also transforming the tools of the trade for professionals. And you mentioned earlier how it dramatically reduces the number of cameras needed. That lower bar for capture must have huge downstream effects, right? Impacting everything from setup complexity to overall cost.
Exactly. Broadcast teams and venue operators can start to fundamentally rethink their camera setups. Traditionally, achieving anything remotely holographic required these massive, expensive, and intrusive camera arrays.
Like the 50-plus cameras for NBA TrueView you mentioned.
Right. But if neural reconstruction can genuinely reduce the camera requirements by as much as 2/3 while maintaining or even improving quality, that changes everything.
How might a setup look then?
You could potentially just augment your existing standard broadcast cameras, the ones already there for the 2D feed, with maybe just a few additional strategically placed ultra-wide angle, high-resolution like 8K cameras.
Okay.
Feed the video from that smaller set of cameras into the AI reconstruction engine like Echo and get a full 3D volumetric feed out.
That makes it feasible in many more places.
Absolutely. It makes volumetric capture potentially feasible in places it simply wasn't before, maybe smaller college venues, or even for temporary installations at specific major events like the Olympics or World Cups, without needing a permanent massive rig.
And less intrusive, too, I imagine.
Yeah, that's a big point for venues and fans. Fewer cameras means less hardware to install, less cabling, and less potential for cameras to obstruct spectator sightlines. It makes getting buy-in for deployment potentially much easier.
Okay, that makes a lot of sense. So once you have this highly efficient neural native data stream coming out of the AI, how does that impact the rest of the production and distribution workflow? Does it simplify things for broadcasters, or does it add new complexities?
It seems poised to significantly streamline workflows in many ways. For the production teams,
Yeah.
instead of managing potentially dozens of individual camera feeds and running a separate, complex, computationally intensive pipeline just to stitch them all together into a 3D video after the fact,
Right.
a trained AI model like Echo does that heavy lifting, potentially in real time.
Mm-hmm.
The output is then this spatial media format.
And can you edit that format easily?
That's the idea. The goal is to have an output format that can be edited much like traditional video. You can cut highlights, create replays, add graphics, except now the video itself is inherently volumetric. You'd need new editing tools that understand 3D space, of course, but the workflow could become much more integrated.
And for distributing it, getting it to the viewers.
From a distribution standpoint, because the neural data is designed to be much lighter and more compact than raw 3D geometry.
Right.
It should fit much more easily into existing content delivery networks, CDNs, that broadcasters already use. It doesn't necessarily require a complete overhaul of the distribution infrastructure.
And does it offer flexibility in what viewers receive?
Yes, that's another potential advantage. You could potentially take that single volumetric feed and serve multiple experiences from it. Maybe interactive viewers with capable devices get the full spatial media stream and render it locally. But for viewers on older devices, or just watching the traditional TV broadcast, you could potentially use cloud-based rendering to generate a standard 2D video feed from that same volumetric source, perhaps even offering dynamically generated virtual camera angles chosen by a director.
So one core feed serves both interactive and traditional viewers.
Potentially, yes. The key is the flexibility of having this rich, volumetric source data in an efficient format. You get both the cutting-edge interactive experiences and the familiar traditional broadcast out of one streamlined, AI-powered pipeline.
This really paints a clear picture of how these direct applications, instant 3D replays, choose your angle viewing, AR integration, easier capture, streamlined production, will fundamentally change your viewing experience as a fan.
It sounds like the future of sports is genuinely about to become profoundly different, moving from watching a static canvas to exploring a living, dynamic environment. It truly feels like we're on the cusp of that. The message coming through loud and clear to sports broadcast teams, technologists, leagues, everyone in the ecosystem is this neural native volumetric video, this spatial media, is rapidly coming of age. It's moving out of the research labs. And it's really time to stay seriously exploring it, experimenting with it, and figuring out how to integrate it.
Because those old limitations are falling away.
Exactly. Yeah. The things that kept volumetric video on the fringe for so long, the massive camera rigs, the prohibitively high costs, the incredibly slow turnaround times, those barriers are actively being dismantled by these new AI-driven approaches.
Yeah.
We are rapidly moving into an era where spatial media could become not just a novelty, but potentially as commonplace and expected as instant replay is today.
That's a bold statement. You think it could be that transformative?
I think the potential is there. Just think about previous shifts. The switch from analog to digital television, or from standard definition to high definition. Each of those revolutionized sports viewing in its own way, right?
Absolutely. Can't imagine going back.
Well, this switch from flat 2D video to interactive volumetric spatial video, it has the potential to be just as transformative, maybe even more so, because it fundamentally redefines the fan experience from passive viewing to active exploration.
So it's not just about better technology then. It's really about rethinking the entire art of storytelling in sports, and even how we capture reality itself. It sounds like it demands a whole new kind of cinematography, a new way of thinking for producers and directors.
Precisely. It opens up entirely new creative possibilities. Producers can start to imagine shots and camera moves that simply aren't possible with physical cameras.
Like what?
Think about being able to instantly freeze a moment in time during a crucial play and then smoothly pan the virtual camera 360 degrees around the quarterback as they release the ball. Or getting a dynamic, stabilized view from just above the goalie's shoulder during a penalty kick, moving with them, all executed virtually on the fly from the volumetric data.
Wow, shots you could never get with a real camera operator.
Exactly. And editors will need new tools, too. Tools specifically designed to cut, manipulate, and enhance volumetric clip software that understands the 3D space, depth, and timing, not just sequences of flat 2D frames.
A whole new editing paradigm.
Yeah. And even camera planning on location might evolve. Cameras might be placed not just for the best traditional 2D aesthetic shots, but strategically positioned to feed the AI reconstruction engine the optimal combination of angles it needs to build the best possible 3D representation. It's potentially a new kind of cinematography, one designed in partnership with the AI.
That's fascinating. And as this technology matures, I guess standards will need to evolve too, so different systems can work together.
Absolutely crucial. As this technology moves from proprietary systems towards broader adoption, having standards for spatial media formats, for streaming protocols, for quality metrics that will be essential for interoperability, and ensuring a consistent, high-quality experience across different platforms and providers. Organizations like the Volumetric Format Association, VFA, are already actively discussing these kinds of issues, trying to figure out how to handle these new neural formats to ensure the ecosystem can grow in a healthy way.
Okay, this is truly a new playing field opening up. So let's try and distill this. What's the bottom line for our listeners today? What's the big takeaway from this deep dive into the journey from volumetric video to spatial media?
I think the bottom line is this. Volumetric video is rapidly evolving, shedding its old heavy skin of point clouds and polygons and transforming into something new: spatial media.
Right.
With neural fields and AI firmly at the helm, what was once incredibly bulky, slow, and expensive is becoming sleek, live, and scalable.
And sports are leading the charge.
Sports seem poised to be the first major arena to truly showcase this incredible leap on a mass scale, potentially turning games from something you watch into immersive experiences that fans can literally step inside and explore.
It's definitely an incredibly exciting time to be watching this space, right at the intersection of cutting-edge technology and passionate sports fandom. The playing field for volumetric innovation is clearly wide open now.
It really is. And the ball, you could say, is squarely in our court, the court of the technologists, the broadcasters, the leagues, the teams.
The teams and companies that get ahead of this curve now, the ones that start embracing these neural volumetric formats.
They'll likely be the ones defining the future of sports entertainment, creating experiences we can barely imagine today.
So the message is, gear up, start experimenting.
Exactly. The era of scalable, live, interactive 3D sports is about to kick off. Welcome to the new playing field of spatial media.
Which leads to the final provocative thought for you, the listener. As this technology rolls out, how will you choose to experience sports in this new spatial media future? Will you become your own sideline director? Will you step into the shoes of a virtual analyst? Or will you just want to step inside the game itself and feel the action like never before? The choice might soon be yours.
A fascinating question to ponder.
What an incredible deep dive today. We've really covered a lot of ground, haven't we? From those earliest data-heavy days of volumetric video with points and meshes.
Right, the marble sculptures.
Through the clever innovations like Gaussian splatting that boosted rendering speed.
The fuzzy blobs.
And then into the truly revolutionary world of neural radiance fields, that idea of implicit representation.
Yeah, the dreaming network.
Culminating in this third generation of AI-driven spatial media, exemplified by systems like Skyrim.ai's Echo, that promises scalability and real-time performance.
It's been quite a journey, technologically speaking. We've seen how what was once this niche, incredibly cumbersome technology is rapidly maturing into a potentially scalable interactive reality, thanks largely to advances in AI and neural representations.
We really hope you, listening, have had some aha moments along the way today, that you've grasped not just the technical details, the evolution from explicit to implicit,
Right.
but also why these advancements truly matter, why this shift towards spatial media is so significant for everything from how we watch our favorite sports to potentially countless other applications that are probably just waiting to be discovered.
Absolutely. And the insights gained from understanding this evolution, this move towards efficient neural 3D representations, they really do extend far beyond just the realm of sports.
How so? Where else might we see this kind of tech making an impact?
Well, just imagine how this kind of technology could reshape remote collaboration. Imagine having truly volumetric telepresence, feeling like your colleagues are right there in the room with you. Or think about virtual tourism, being able to explore a remote location immersively, not just through 360 photos, but in full volumetric 3D.
Yeah, or training simulations.
Exactly. Medical training, complex equipment operation, being able to practice in a realistic, interactive 3D environment could be incredibly powerful. Or even how we preserve and interact with history, capturing historical moments or artifacts as spatial media that future generations can explore.
The possibilities really do feel limitless once you break free from that flat 2D window.
They really do. So we definitely encourage you, our listeners, to keep learning about this rapidly evolving field of spatial media. Think about the ways it might impact your own work, your hobbies, your world. It's developing incredibly fast.
It certainly is. Well, thank you for joining us on this particular deep dive into the future of immersive experiences. We hope you enjoyed the exploration.
It was a pleasure. Thanks for listening.
Skyrim.ai was founded by veterans of the spatial media industry and is committed to advancing the field of immersive sports experiences and storytelling to fans everywhere.